Okay, we're at the last section, the RLC circuit. Last time we looked at the oscillation between an LC circuit, and you could see that it energy transferred between the capacitor and the inductor. That was a very idealized circuit, and we're going to have a little more realistic view in this section. Let's look at the power point. The switch is set first to position A and the capacitor is charged. So you charge the capacitor, then you switch to B, and now the oscillation begins between the capacitor discharging and storing magnetic field in the inductor, the magnetic field collapsing and charging the capacitor and just oscillating back and forth. You should have seen, or you should play with the Walter Fendt demonstration to look at it. To get a feel for it. But now we're adding a resistor, and resistance is you're never going to get an idealized circuit because there's resistance in the wires. There's certainly resistance in the coil because it's made out of wires, and so there's resistance in the coil. So there's always going to be some resistance. But here we're actually going to add a resistor and see what the result is. So basically, you've conservation of energy. It's the energy. The change in electrical energy plus the change in the magnetic energy stored in the inductor plus the internal energy of the resistor all equal to 0. Well, let's differentiate each one of those, and you get QC dQ dt plus Li di dt and plus I squared R, which I squared R is just the, if you recall, the power to the resistor. That all equals to 0. So there's going to be an exchange of energy of all these. There's going to be conservation of energy. Now we know dq dt. Let's start with first looking at that first QC dq dt. Well, dq dt is equal to I. So basically that's QCI plus Li di dt plus I squared R equals 0. Now let's divide or take out an I from each term. So you're left with QC plus L di dt plus IR. And we learned in the last set of slides that di dt, since I is dq dt, di dt is really d squared q dt squared. And if we take that information and rearrange everything, we have L d squared q dt squared plus R dq dt plus QC equals 0. Now, this is the same equation. That is similar to the equation for a damped oscillation, where M is the mass, X is the position, B is the damping constant, the damping coefficient, and K is the spring constant. So we're relating these, and Q is equal to Q max e to the minus RT 2L times cosine omega t. That's the relationship to the equation up at the top. Let me get rid of that. Okay, so omega d is equal to 1 over LC, which is 1 over LC, if you recall, is our related to the oscillation, and it minus R over 2L squared. All of that, you take the square to the 1/2 power is the same as the square root. And so let's look at the analogies between the RLC circuit and the particle damped harmonic motion. The charge is Q, the position is X, the current is I, the velocity is Vx, the potential difference is delta V, the force is, or Fx is the force, resistance is R, B is the viscous damping coefficient. The capacitance is C. 1 over K is the spring constant. And the inductance is L, and the mass is M. And then you see the currents, the comparisons, the equation comparisons here. I equal dq dt, Vx equals dx dt, rate of change of current equals the second time derivative of charge. Acceleration is the second time derivative of position. Energy in the inductor and kinetic energy of a moving particle. Energy in a capacitor and potential energy stored in the spring. Rate of energy loss to resistance, I squared R, and rate of energy loss due to friction is damping coefficient times V squared. So in an RL circuit, you have L d squared Q dt squared plus R dq dt plus Q divided by C equals 0. And that's equivalent to the particle in the damped motion, mass times mass times acceleration. Acceleration is d squared x dt squared plus b dx dt plus kx equals 0. And you'll see that the Q versus T curve it represents a plot of equation 31.26, and there's an oscilloscope photograph of the damped oscillation. R is equal to the square root of 4 times LC. Before we get to that last slide, let's look at go back to Walter Fendt and see what happens when, let's see, where is, oh, here he is. So we were looking at this earlier. We had let's reset it and start it, and it goes back and forth, and it'll go back and forth for a long time. But now let's reset it. But let's put in just like let's just put in a 1 ohm resistor and reset. You can see that we put in a little resistor there, and let's start. And it doesn't look very different, does it? But now let's pause it. Let's make this a 10 ohm resistor. Let's see, reset, make this a 10 ohm, and start it. Oh, now you can start seeing that each subsequent oscillation is reduced because of the resistance. So if we make it something like, let's make it a 50, and you can see it doesn't get very many oscillations. Let's say speed it up. You can see that what's happening? Well, you're losing some of the energy to heating up the resistor. Let's reset it. Let's make it something like 25. We'll get a little more, a few more oscillations. But you can see that it's damped, and it's damped according to that diminishing curve that they showed you in the, and it's all practically all gone. The diminishing curve on this last slide, let's show it again. Yeah, you can see there's the diminishing curve. And let's, so here they're just showing you the introductory photograph and explaining what's going on. The circles are the loops of wire buried under the street. So it's connected. The connections to the loops are those straight wires going to each circle. There's some on the other side for each lane. The control electronics drive the RLC with oscillating voltage so that the circuit oscillates at a natural frequency. When a vehicle stops over the loop, the inductance of the loop changes for 2 reasons. The metal of the car represents a magnetic material which alters the magnetic field passing through the loop. So the eddy currents induced in the metal car produce additional magnetic field lines that pass through the inductance loop. So the change in inductance L of the loop changes its natural frequency of oscillation, and the control electronics detect this change. It sends signal to change the light from red to green. I know I've heard complaints like from some motorcycle riders that it would never change for them. It almost had to wait till another car came by because there was not enough metal mass in their motorcycle to trigger the sensor. Not enough metal mass. But anyway, that ends the chapter and the section. So we'll stop